So let us now look at a mathematical model of this demand for network goods, right? So typically we are going to think that the benefit a consumer gets, or in technical terms, the utility that a consumer gets from using a particular unit of the good as follows. So we are going to say that Uij is the benefit going to consumer I uh, from using good J. So that's going to probably be composed of two different parts. So you have got one part which does not depend on the network effect. So let's call that AI. So this is basically, think of this as the standalone benefit, and this comes from the immediate use of the technology. So imagine that you have phones, you use phones for perhaps communicating with others, but you can use phones for other things as well, right? So think of these other things as the part which is this AI. And then, because we are thinking about modeling the demand for network goods, there's going to be a component of the consumer's overall benefit that comes from the fact that he or she expects a certain number of users to be using this particular good, right? So that second part, the part that is the network effect, is going to be captured through this equation, which is Fi as a function of NJE, right? So what is NJE? So this is the expectation of how many people is going to be using this good NJE, and different consumers may value this different network effects differently. So that's why you have got this F, which is a function of I, right? So different people may have different F functions. So what are the reasonable assumptions to expect when it comes to this network goods that we have been talking about? So one standard normalization that you can do is to imagine that if nobody uses the good, if that is the expectation, then this network effect should just be thought of as zero. But higher the number of people that are going to be using goods, you would expect that this is going to be increasing this Fi function. And as a result of that, the consumer's payoff from using that good, or the utility from using this good, is going to go up, right? So the expected number of consumers in the network increases the utility from using this good. And we'll see that this is actually a very rich framework, and it can in fact be used to model both direct and indirect effects, right? Why? Because imagine that we are first talking about the WhatsApp versus the Telegram example. So the more the number of people we expect to be using WhatsApp and Telegram, right? So the more my benefit will be from being on, let's say, WhatsApp or Telegram, right? So if I expect a lot of people will be using WhatsApp, then my benefit from using the WhatsApp is going to be an increasing function of the number of people who will be using, right? What about the indirect effects? So imagine that I am thinking of buying Mac OS. So if a lot of other people are also using Mac OS, then there is more incentive for the developers to actually produce software that can be used in OS, and therefore Mac OS. And therefore, my utility from using Mac OS is going to go up, right? So it can be used to model both direct and indirect effect. One important question is going to be, how should we think about modeling expectations, right? Because you can see here that the payoff from using the good depends on the number of people who are expected to be using that good, right? So we'll see that there are two standard ways of thinking about how to model expectations, and we'll both use them depending on what particular context that we want to think of, right? So one way of modeling it is what is known as fulfilled or rational expectations. So here, basically, consumers are going to be forward-looking, and they are going to base their current purchasing decisions on the expectation about the future network sizes, right? But in order to make this tractable, because you can have a lot of like different types of expectations about the future, we are only going to be focusing on the case where the expectations that the consumers make are going to turn out to be correct, right? So that is the origin behind the word of rational use here, right? So they are doing the best that they can in terms of their expectations about the future. The second type of situation that we'll be doing are what are known as myopic expectations. So here it's myopic in the sense that consumers are not going to be forward looking, but they are going to be basing their decisions only on the current actual network sizes when they're deciding whether to adopt a good or not, right? So often for tractability purposes, we'll see that this is actually turns out to be much easier to model than the rational expectations, where you have got that consumers are far-sighted, right? So these are in some sense two extreme cases, one where consumers do not look in the future at all, and in the other case where consumers not only look in the future, but whatever expectations they have about the future turn out to be correct, right? So we'll see the uses of both of these modeling techniques. Okay, so let's go back once more to think about this heterogeneous network effects. So remember, this is the network effects that we have, where Uij can be the consists of two parts, AI plus this network effect, and we can have various different versions of this model, right? So one version that you can have is that the benefit that the consumers get, the standalone benefits that the consumers get, can differ according to the different consumers, whereas the network effects are the same for all the consumers, right? So this would be an example where you've got heterogeneous standalone effects, right? So notice that I am indexing each consumer by a variable theta, right? And I'm saying that for each of the consumers, the network effect is the same. Notice that this network effect term, which is V multiplied by NE, where NE is the number of people expected to be using that particular good, that does not depend on theta, right? So two different consumers with two different theta, they will agree on the same network effect, right? However, the standalone benefit, which is this first part, which does not depend on the number of other people using it, that may differ according to the different consumers, right? So this would be an example where basically what you have here is that you have got different AIs, but this second part is the same for all the consumers. But you could have also done it the other way around. You could have had a case where the standalone benefits are the same for all the consumers, right? But the network effects are different for different consumers, right? So again, two different consumers with two different values of theta, they will, in this first example, have two different network effects, because the network effect part, which is V multiplied by the number of expected people, that is multiplied by theta. So if you have different values of theta, then you are going to have different values of the network effect. But the standalone benefit, which is this A, that does not depend on theta, and therefore that is the same for all the consumers. And this is actually a pretty rich framework already, because, for example, it can be used to think about consumer electronic products, right? So these are often characterized by sequential adoption. So basically what you have in this sort of industry is, first you have got initially a lot of users who are kind of like maybe thinking of buying this, but only a few users actually buy. And over time, what you would find is that as more and more kind of like people are buying, you have got basically the purchases going up, right? So in this case, you've got a minor number of early adopters, right? A small number of them. And we can think of these as basically people with a high value of theta, right? Now, one question might be, okay, are we talking about the high value of theta in this heterogeneous network effects, or are we talking about heterogeneous standalone benefits? It turns out that depending on the reason why you might think that there are some early adopters who are keener to adopt the new network good, depending on the context, you can have both, right? So historical examples, let's talk about two. So BlackBerry was kind of like a communication device, right? So there it was something that was used to kind of communicate with other people, right? So you could send emails at any time and anywhere. And so the early adopters here were basically people who valued highly the possibility of reading and sending emails at any time and anywhere, right? So basically there were people, some of them had a very high value of theta in the sense of having a heterogeneous network effect. So they valued the fact that they could communicate more with others. And obviously, this network effect is increasing in the number of other users who are using BlackBerry as well. And therefore, for them, these were the early adopters, right? The people who had a high value of theta, where the theta was associated with the heterogeneous network effects. However, in another example, which is high definition television, there the early adopters were the people who were the tech aficionados, right? So these were basically people who were very interested in having access to superior picture quality. And so therefore, this was an example where you have got basically not the people had different valuation of this network effect, but you had got different people with different heterogeneous standalone benefits. And the people who had higher standalone benefits from using the product were the ones who first adopted the product, right? So these are again two different examples where you can see these two different things can be kind of modeled in the same framework, right? Okay, so let's now move on with our model. We are going to take a step back and first imagine a model without any network effects. Now, you might ask, why are we doing that? Basically, we'll see that this makes it easier to kind of contrast it and understand better what is the effect exactly of economy on network effects. This would also help us to recap basic supply demand framework, which some of you might have seen before if you have taken a course in economics, but even if you have not, think of this as a very high level introduction to supply and demand, right? So we are going to consider how the market functions when there is no network effect. And what that means is that when we say that there is no network effect, it means that consumers do not basically care about how many other users of the good there are, right? So this is our basic definition of network effects that we are going to do. And what we want to see is how does this market contrast with the market when there is a network effect present. Now, as you might have studied before, basically the way in which we model markets in an economy is to think about it in the context of supply and demand. So first, let's focus on the demand or the consumer side, and then we'll model supply side here in a very straightforward manner. Okay. So imagine that you are talking about markets with a huge number of potential purchases. And each of these purchases are small enough in the sense that they cannot actually make individual decisions which would affect the aggregate behavior, right? So these are basically known as price taking assumptions. So the idea is very simple. When consumers are deciding how much of a good to purchase, they do not anticipate that their own individual decision in isolation is going to be have the ability to actually affect the overall price, right? It's as if, I'm going down and purchasing a television, or I'm going to go down and purchase a potato and everything. So that is not going to probably have any effect at all on the market for potatoes, right? In the sense that that alone would not be enough to kind of change the price of potatoes or price of televisions in a significant manner, right? Okay, so how are we going to think of consumers? So we are going to represent them as a set of all real numbers in the interval strictly between 0 and 1. So this is basically modeling consumers in a continuum manner, and you'll see that has its advantages in this context, okay? So think of all the real numbers that are there between 0 and 1. Each of these real number is going to be representing a single consumer, and each consumer is going to be represented by a different real number, right? So you have got this one-to-one basically correspondence, right? And what this means is that we want to think of the total mass of consumers is normalized to 1, right? So it would make sense to talk about 0.6 consumers, in the sense that think of it as 60% of the consumers, right? So what are we going to think of the set of consumers with names between 0 and, let's say, 0.4? So that's basically going to represent 40% of the population that we are talking about, right? So that's how you should interpret it, right? So you should not think of each consumer as the number of consumers, but think of these consumers with different names as thinking of representing fractions of population, right? So that's where the benefit of kind of this approach comes from. Okay, what do we know about each consumers? So they want at most 1 unit of the good, right? So they either want 0 unit of the good or 1 unit of the good, but they do not want more than 1 unit of the good. And because we are talking about an economy without any network effects, so each of these consumers has a personal intrinsic effect in obtaining the good that varies from one consumer to another, right? So they care about the good, not because they care about other people using the good, but they have some inherent benefits that they get from using the good, okay? Now, how are we going to think of each consumer's particularly, how much they value having the good? So that is represented by a single number, and that single number is basically the reservation price. So what is the reservation price? So this is the maximum amount that the consumer is willing to pay for 1 unit of the good. Remember, the consumer either wants 0 unit or 1 unit. There is going to be a maximum price above which the consumer is not going to want the good. So that this reservation price basically says what's the maximum amount that the consumer is going to pay for the good. Okay. Now, let's go back to how we are thinking of the consumers. Remember, we are thinking of each real number between 0 and 1 as representing one consumer, and each consumer is being represented by the 0 and 1. So let's assume that the way in which we have labeled the consumers is that we have basically arranged them in the order of decreasing reservation prices, right? So what that means is that Miss 0.2 has a higher reservation price compared to Mr. 0.5, right? So basically, Miss 0.2 is willing to pay a higher price for the good compared to Mr. 0.5, right? So that's the way in which we have ordered the consumer. So higher is your real number label, right? The lower is your basically willingness to pay, right? And so now we can basically represent this as a function as well, right? So give me any consumer X. So this X will be the real number that is associated with the consumer X, right? So it can be any value between 0 and 1. I'm going to basically specify what is the reservation price of the consumer using this function R of X, right? So this is R of X is basically our reservation price. Now, based on what we have said, we are going to basically assume that you've got this R is a strictly decreasing function. So higher the value of X, the lower your reservation price is. And just to make things tractable, let's also assume that this function R is continuous, right? This will kind of like just help us to simplify our world without causing any necessary technical problems, right? Okay. Now, so this is like how much they are actually willing to pay, right? But how much they actually have to pay depends on the market price, right? So suppose that you have got each of these consumers, they go down to the market and say they see that this good that they are interested in purchasing, the price of that good is P, right? Now the question is, which are the consumers who are going to buy this product, right? Now, everyone who wants to buy this good can buy at the price P, right? That's what it means in the sense that the market price for a unit of the good is P, right? And there's going to be no units that are going to be offered for a price below P, right? So at this case, how are we going to think about it? So everybody whose willingness to pay is at least P, right? Whose reservation price is at least P is going to end up actually buying the good. And everybody whose willingness to pay was below P will end up not buying the good, right? So this P is basically going to act as a cutoff. If you are willing to pay more than P, then you will buy the good. And if you are willing to pay less than P, then you are going to not buy the good, right? So remember, we have arranged the consumer in the decreasing order of their reservation price. So that means that the highest price that anybody is going to pay is R0, right? So at a price of R0 or more, so suppose the price was more than R0, which was the higher than any willingness to pay, then in that case, nobody will buy the good, right? At a price of R0 also, there's also going to be anybody who is willing to buy the good, because remember, there is no consumer who is labeled as 1, right? Because you have got all numbers which are lying strictly between 0 and 1. What about a price which is R1 or below R1? In this case, everybody wants to buy the good because basically the reservation price of all the consumers are going to be above than the market price, right? So these are the two extreme cases. And we can think about the intermediate cases where imagine that the market price is some number which is strictly between R1 and R0. Based on the continuity assumptions and the fact that this R function is strictly decreasing, what that means is that then therefore there must exist some unique number X with the property that Rx equal to P. And the way then you'll interpret it is that everybody who is between 0 and X, they want to buy the good, and everybody who is above X, they don't want to buy the good. Why is that? Remember, we are basically kind of like arranging the consumers based on their reservation price. So if you are between 0 and X, that means your reservation price is higher than Rx, which is equal to P. And so therefore you want to buy the good. But if you are above than X, then your reservation price is less than Rx equal to P. And therefore you would not want to buy the good, right? And another way of interpreting that all the consumers between 0 and X buy the product, remember, means that X fraction of the population buys the product. So we can also think of this graphically, right? So we have got these two extreme cases, R0 and R1. If the price is above R0, nobody is going to buy the good. If the price is below R1, then everybody is going to buy the good. And for each of these cases in between, suppose you fix a price P, then you can use this diagram y equal to Rx to actually say what's the number of people who will end up buying the good, right? So this will exactly be those people whose reservation price from buying the good is more than the price P, right? So this is for a particular value of P. You can actually do this analysis for all values of P between R0 and R1. So what that means is that you end up getting correspondence, right? So you end up getting that for each value of P, there is going to be a value of X which specifies what's the fraction of people that will make the purchase at a price P, right? So imagine that you chose a price which was above this P. So you chose a price somewhere here. Then the number of people who will end up buying the good is going to be given by this fraction, which is less than this X. If you chose a price below P, let's say you chose a price P here, then you end up getting the higher fraction of people who will end up buying the good, right? And you can do this exercise for each value of P that you are interested in between R0 and R1, right? So this relationship between price and quantity, right, which says that for any price that you can think of, what's going to be the quantity that's going to be demanded is what is known as the demand for the good, right? So this is the demand part of demand and supply. And what this function R does basically is to kind of describe the what is known as the inverse demand function, right? Because it is R, which is a function of X, and X is basically the demand, right? Okay, so the inverse of R, which means that for each value of P, what is the value of X that you get from this graph? That is basically what is known as the demand function, right? So that's the demand part that you often hear about. Okay. So this is the demand part. Now we want to think about the supply part, but we want to keep the supply part as simple as possible, right? Why? Because remember, this is the situation where we want to actually model and think about the world without network effects, because we want to contrast it with the network effects. And when it comes to network effects, all the interesting thing that is happening is in terms of different consumer behavior, right? So the demand side is important. So that means that we'll focus on enriching the demand side, but we'll keep the supply side as simple as possible. So in economics and game theory in general, so basically the simplest possible supply side model that you can have is that you've got a lot of producers who are all willing to produce the good at some constant cost of P star per unit, right? So think of this as a parameter here, right? So there is some value of P star, It can be some particular number, and this good can be produced by however number of producers are there at a constant cost, right? As before, we are going to be dealing with the price taking assumption. So assume that there are many potential producers of the good, so that none of them are large enough to be able to influence the market price of the good. So we'll see how you can relax this assumption later on. But for now, none of the producers are big enough. So they take this P star as given and they decide how much to produce at that value of P star, right? Okay, so what does it mean when we add up all the producers? That means that if the market price is P star, then the producers are willing to supply whatever is the market demand. However, if the price falls below P star, then the producers are no longer willing to produce anything, because then they are going to be making losses on all the items that they're producing, right? Because remember, their cost is P star, right? So clearly the price cannot fall P star in this market, cannot fall below P star. But can the price remain above P star? Well, that's also not possible in this model, because basically if the price remains above P star, then the producers can compete with each other by just kind of like reducing this P star, right? So we basically end up with a situation where you have got then therefore that the market price is going to be P star, and we get that from the supply side, right? Again, just to make the model tractable, let's assume that the P star that is given as a parameter here lies between R0 and R1. Why is this a good assumption to make? Because again, you have got that if P star is above R0, then nobody is going to be buying the good, right? So this will have an equilibrium where you've got that the equilibrium quantity in this market is going to be 0. And if you've got P star below R1, then everybody is going to end up buying the good. So these are not that interesting cases. So we are going to be dealing with a situation where P star is between R0 and R1. Okay. All right. So this basically determines the supply of the good, right? So the supply of the good is very simple in this model, that you have got P star at that price P star, suppliers are willing to produce as much as possible, right? Okay. So because P star lies between this R1 and R0, we can always end up finding a unique X star given our assumptions that we have made, so that Rx star equal to P star, right? And then this X star basically is the equilibrium quantity of the good in this market, given the reservation prices and the cost P star, okay? So we can again represent this graphically. Remember, this Rx was the inverse demand curve on the basis of which we could have derived the demand curve. And this P star is a parameter that is given to us. Recall that this is a bit different from the way in which we had derived the demand curve, right? In the demand curve, we had said, okay, give me any value of P. I can find out a corresponding value of X, so that X will be the quantity demanded, right? I can take any value of P I want between R0 and R1. I'm going to get a value of X which lies between 0 and 1. If I take a value of P above R0, then the value of X is 0. If I take a value of P below R1, then the value is going to be 1, value of X. So that is an exercise where I was doing, where I was free to vary the P. Here, I'm going to be fixing P star. This is the parameter. And I'm going to be asking at that cost of production, what's going to be the equilibrium price, which is going to be P star because of the reasons we talked about. And what's going to be the equilibrium quantity? We can see that at that P star, how much is going to be the demand, which we can get from this inverse demand curve, Rx. So the value of X star, so that Rx star is equal to P star, that's going to be the equilibrium quantity. Okay, so X star represents equilibrium in the sense that if you had less than X star fraction of the people purchasing the good, then this would not be a situation that can be sustained. Why not? Because imagine that you had this X being less than this X star. So that means that you basically had some people who had a reservation price higher than the P star, which was the price at which they could have purchased the good, but they're still not purchasing the good, which does not make sense, right? Basically, we are saying that then there are some people in the economy who are willing to pay, let's say, 50 rupees, whereas the price at which they are willing to get they can get the product is 30 rupees, right? So in this sense, it would make sense for them to go and buy the product, because remember, there are these producers who are all willing to supply the good at a price of 30 rupees, right? So this cannot be an equilibrium. Can we have an equilibrium which is the opposite case, where you have got more than extra number of people buying? So that cannot also be the case, because then you would have had at least some people who then are purchasing the good at a price which is more than their reservation price, which again does not make sense. So imagine that the maximum you were willing to pay for the good was 20, but you were still purchasing it at 30. So without any subsidies or anything, this does not make any sense, because then you are basically paying more than what your maximum willingness to pay is, right? So that also does not make any sense. So in all of these cases, if you have got X less than X star, there's going to be an upward pressure on the consumption of the product, right? Or if you have got X star more than X more than X star, then there's going to be a downward pressure on the consumption of the good, right? So you are going to basically have forces which are going to push you back to this X star as the equilibrium price, right? Okay, and another feature of this equilibrium that we are going to kind of like think about later on is to think about the welfare properties, right? So in that case, we want to think about, okay, this is specifying a particular price and equilibrium quantity in the market. So, but is this a good allocation, right? Now, whenever we are thinking of whether this is a good allocation or not, what we want to think about it is whether this is good from the market participants' perspective, right? So then we want to think about what are the benefits that are going to each consumer, right? And each producer from this particular equilibrium quantity and price. Now, from each producer's perspective, things have been simplified here a lot in the sense that, they are basically all producing it at the cost of production. So essentially their profit is zero, right? So from their perspective, it does not make much sense if you have got anyway P star. So that is not our concern. But we can think of what is the welfare going to the consumers. Now, why is there a welfare that is going to the consumers? Because you have got basically some people who have a higher reservation price compared to the price that they're paying, right? Remember, this is the price P star at which the good is going to be sold in the market. But you have got basically a set of people who had a higher willingness to pay than this P star, right? And so therefore you end up with with a set of people who are between the 0 and X star, who have a higher reservation to pay, who have a higher willingness to pay than the market price. So in some sense, they end up getting a surplus, which is equal to their maximum willingness to pay minus what they actually end up paying, right? So this is the willingness. And from a societal perspective, basically the benefit of a trade in the good comes from the fact that the good is going to somebody who has a willingness to pay, which is more than basically the cost of producing that good, right? So that is how you can think of generally as the social welfare of the allocation, right? Now, let's think of like two questions. Let's break this up into two questions, right? One question is that suppose you decided to actually produce X units of the good, right? Then who should you end up giving this good from a welfare perspective? So the answer to that question is that from just a welfare perspective, not from an equity perspective. If you do not care about inequality and all these things, you just care about efficiency, then you should end up actually giving these goods to the people who have the highest willingness to pay for this good. Why is this the case? Basically, you can think about this case. So the maximum, remember, the way we are thinking of the benefit to the consumer is that this is the difference between their willingness to pay minus the price they actually pay, right? So the maximum benefit is going to the person who is very close to zero, right? So because this gap between the willingness to pay and the actual price paid is the highest for this person, right? And then as you kind of like move along, then you still have a positive surplus that is going to each consumer, but this surplus is kind of like decreasing, right? So you want to basically then end up going to give the good to the people who have the positive benefit, right? Positive surplus from consuming this good. And these are basically the set of people who are basically those whose rank is between 0 and X, right? So if you had only X amount of good to allocate to people, give it to those whose reservation price is the highest, which in our model means the set of people between 0 and X, right? That's the set of consumers you want to give to. So that answers one question, which is that suppose you are producing X amount of good, who should you give the good to if you want to maximize social welfare? The other question to ask is that what should be the value of X, right? So in the first part, we didn't answer this question. We said that suppose you have decided on a value of X, who should you give the good to? The second part answers this question, what's the value of X that you should choose, right? So how should we think about it here? So as I argued before, that from a producer's perspective here, the surplus is zero because you are going to essentially sell the good at whatever is the cost of producing the good. But we can think of what is the benefit then to the consumers of these different allocations, right? So imagine that we had decided to, this was the P star, this is the price of that good. So imagine that we had decided on a lower value of X. Now, this would not have been optimal because you would have had a situation basically that you had a situation where the reservation price or the willingness to pay for the good is higher than the price of the good, but we are still not kind of like selling that good, right? In that case, basically, we would have had people whom you could have produced the good at a price P star and given it to them and generated a positive surplus, right? So we are leaving some surplus on the table, and this would be the case for all values of X, which is below X star, right? So definitely, if we want to maximize the size of the pie, we should not choose a value of X, which is below X star. would we benefit from having a value of X higher than X star? No, because then you are basically giving someone the good at a price which is which is above their reservation price, right? So somebody had a willingness to pay of 20, you are producing the good at a price of, let's say, 30 and giving it to that person. It does not make sense because it costs more to the society than what that person is willing to pay, right? So basically, in this situation, you again end up with a situation that the maximum willingness, the maximum social surplus is maximized by choosing the value of X star that we exactly found. So it's socially optimal in that sense. So I think we'll have like more opportunities to discuss this a bit later, and you can look into the reference if you are more concerned about this. But this is like a very standard way of thinking about whether an equilibrium is socially optimal or not. So think about it from the benefits of the consumer and the producer separately in this manner, and then add them up. That's the way in which social welfare is one of the standard ways in which it is measured in